Now we're going to look at another type of test, and this is one that deals with proportions. So instead of estimating the mean, such as the mean is equal to 52 or the mean is equal to 576, some number, now we're saying the mean that we're looking for is a proportion. So it's p. And what's tricky about that is we already have something called p, which is our p-value. So now we have another p that's kind of getting mixed into this. But really what we're talking about is our proportion. So we'll get into the symbols and try to make sure we can keep that all straight. And I'll show you how to determine the difference in your calculator so that you don't mix up your p-value with the estimate of the proportion. So let's start out with an example to help explain what's going on. A national poll stated that 41%, and that percent again referring to a proportion, of Americans approved of the president. You believe that is lower in your town, so you conducted an SRS of 90 people. 31 of them approved of the president. Have you shown a statistically significant difference? You'll notice that the way this is written and the way I talk about it, we didn't rewrite this as a percentage right away because our calculators actually will want to just have the raw numbers, that 31 out of 90. So instead of saying, oh, what's 31 divided by 90? It's roughly 34% or whatever it might be. We're going to leave it just like this. Now what you want to determine is this number, is this fraction that you found statistically significant and different enough from this number or not? One thing that we didn't have to do when we were dealing with standard hypothesis tests is do any kind of check, any kind of thing to make sure our numbers are going to work. However, when we have a proportion, we need to check that we have at least 10 successes, or 10 people who say yes, and at least 10 failures, or people who say no. Now, if we look at our numbers, we have 31 out of 90. Now, with 31 out of 90, what we're saying is that 31 people said yes, they did approve of the president, and the rest of them, which in this case would be 69, or 59 people, would not approve. So they would say no. So both of those numbers are at least 10. And that's what you're checking for. Is this value here, which is x, is that going to be at least 10? Yes. Now, is the number of people left to get up to 90, the total, is that large enough? In this case, it's 59, so that's plenty more than 10, so we don't have anything to worry about in this particular problem, but that's always something to watch for. So we passed that first check. Now we can go ahead and do our null hypothesis. That is that the proportion is what they claim. Now they claim that it is 41%. So for our null hypothesis, we are going to say that the population proportion, P, not mu this time, we're going to call it P, is equal to 0.41. You believe that it is lower. So therefore, you think that it is less than 0.41. So P0 is less than 0.41. Again, that 0 just means it's a hypothesis. It's a null hypothesis. So we're going to leave that as P0 less than 0.41. At this point, we have all the numbers we need, and we just need to go straight to the calculator. So this initial part might have been a little bit confusing, but the next part is the rest is just punching in values. So we go over to our stat tests, and we go down to one prop z test. You'll notice that it's z and not t again, but for real data, the z test will work when we're dealing with proportions, so z is just fine. We go to our one prop z test. Our p0 we said is equal to 0.41, so we type in our 0.41. And then we go down. Our x is the number of people who said yes or approved. 31. Our n is the total number, which we said was 90 people that we talked to in our sample. And now, is our proportion greater than, less than, or just not equal? Well, we said it is less than 0.41. So we're going to go choose the second option here. And then we're going to calculate, and we're going to get a p-value back. So let me drag that over here. The one prop z-test is going to say that the proportion, we're testing that the proportion is less than 0.41. Our p-value, the value that we've always been looking for, is going to be 0.103 here. This other p, it's got a p hat. It's got a little squiggle on top. You can barely read it on here, but that's p hat. That's referring to the estimated proportion that you calculated. That's 34 divided by 90, which is 0.344 repeating. So for now we're going to ignore that. The main thing that we care about is this value of p right here, the regular p, the first one to come up. So at 0.1, have you shown a statistically significant difference? Even at a 0.10 alpha level, we would have just barely missed it, and at 0.05, we missed it by quite a bit. So no, we fail to reject. We do not reject the null hypothesis. We do not have statistically significant data in this example. So fail to reject using our proportion test. Let's try another one, except this time let's compare two proportions to each other to see if they're different, kind of the way that you would compare two sample means and see if they are different. To see which gender was more hygienic, you conducted a study of how many people brush their teeth at least once a day. In an SRS, you found that 25 of 25 women, you found that 21 of them brush their teeth every day. So 21 out of 25 women. In the same sample, you took a large sample of men and women. You found that 22 men answered the survey, and 14 of them said they brushed every day. So 14 out of 22 men, 21 out of 25 women. Is one gender statistically significantly more hygienic than the other? Well, again, we always remember to do our check. You'll notice that when we have a two-prop test, we don't look for 10 and 10 successes, 10 failures. We look for 5 in each. Now, mentally, you can say, oh, well, 5 times 2 is 10, so it's kind of easy to remember as a rule. If I need 10 to check for in one proportion, 10, then when I have two proportions, I need 5 for each of them, so it adds up to 10. So that's just the rule. The reason this is that if you don't have this, it causes your graph to not be normal enough to use the z interval. So that's why we need this minimum in here. Now, if we look at this, we have 21 out of 25 women. That means 21 say yes, that would be considered a success. And then we have only 4 who didn't, who were failures in this example. 4 is less than 5. Therefore, we cannot do this test right now. So, in this case, you would just say, we cannot do inference because we don't have enough failures in the sample. Going on to the next example, let's do this same problem with a very slight modification. We have a sample of 25 women, but this time it's only going to be 19, which will meet that minimum threshold that we talked about. So this sample, 19 out of 25 brush their teeth every day. And again, we have 22 men, and it says 14 out of those 22 brush their teeth every day. So we want to see if one gender is more hygienic than the other. Let's get our numbers down right away. Our x1, we're going to say is, oops, fix that, so 19 of the women brush their teeth, which means that if n is equal to 25, 6 did not brush their teeth every day. In the group of men, we have 14 brush their teeth every day, so 14 here, and then 6 of them did not, which gets us to our total of 22 men in the sample. So we have these 4 numbers. Next, we need to have our null hypothesis. Well, our null is always that 2 things are equal to each other when we're dealing with 2 things. So we would say that proportion 1 is equal to proportion 2. Now, proportion 1 in this case is the women, and proportion 2 is going to be the men. Now, again, does it matter which order you pick? It does not, as long as all your data is consistent with that. The alternative hypothesis, you want to see if one gender is better than the other, but you don't have a particular one in mind. So therefore, it's going to be a not equals test. Now we need to take out our calculators again. And let's go ahead and punch in these values. So we go to stat, we go to tests, and this time we go down to 2 prop z-tests. That's the 6th one down. So just like the 1 prop, except this time we have 1 extra proportion that we're dealing with. X1 we said was 19, X2 25, or N1 was 25, X2 was 14, excuse me, and then N2 was 22. We're doing a not equals test, so I'm going to select not equals, and then we're going to calculate. Let's drag this over here. So it's a 2 prop test. We're saying that P1 and P2 are not equal to each other. That's our alternative hypothesis. And again, we have all these different forms of P here, but the only one that we really care about is going to be this one right below Z here, the 0.355. That is our P value. These other numbers are estimated proportions that it calculates for us. So, at a p-value of 0.35, is one gender statistically significantly more hygienic than the other? Well, no, we cannot conclude that, because there is a 35% chance that the null hypothesis that men and women are the same here, for their how hygienic they are, there's a 35% chance that that's actually true. You can't reject that with such a high probability of it being true. So, usually, again, 0.05 is that magic number that we tend to use. Or something else you could pick ahead of time, but 0.35 is not going to qualify.